Welcome back to video 6.2. Today we're going to work on writing electron configurations. So when you're writing electron configurations, remember that electron configurations are the arrangement of electrons in the cloud. And remember that we're going to be using the Aufbau principle, which states that each electron occupies the lowest energy level orbital available. So you'll want to have your Aufbau diagram handy because we're going to refer to it a lot. And then we have the Pauli exclusion principle, which basically says that electrons in the same orbital have to have opposite spins. And Hund's rule, and I call this like the church bus or the school bus rule. Basically, every electron is going to get its own seat before it starts pairing up. Think about it when you get on the bus to go to like an away game or something with your church. That everybody like grabs their own seat in the church bus or in the school bus until you have too many people and you have to start pairing up. So, when we're writing orbital diagrams and electron configurations, we have to first start off with how many electrons are there. So, I first find oxygen on the periodic table and I see that it has 8 electrons. So, I'm going to write its orbital diagram. I'm also going to write its electron configuration. So, when we look at this, we're going to start off and I look, okay, it's got 8 electrons. I look at my Aufbau diagram and I start at the top. Remember, you always start at this top right and go to the bottom left. So I'm going to start, and in the 1s orbital, I can put 2 electrons. So I draw the 1s orbital and I label it. Remember, the 1s orbital, s orbitals, there's one of them. It can hold 2 electrons. So now I have 6 electrons that need a home. That arrow, that line going down through the Aufbau is now done. So I'm going to start on the next line going through the Aufbau, and I'm going to go to 2s. I've still got, even though it's 2, there's still only one orbital in a 2s sublevel. So I'm going to put my arrows, one up, one down. Those arrows stand for electrons. And so the 2s orbital is now full. Then, so I've still got 4 electrons left. So then I'm going to draw my 2p orbitals. Remember that p orbitals, there are 3 of them. So I draw 3 lines. I label that the 2p orbitals. Those are all the 2p orbitals. And it can hold up to 6 electrons. But do I have 6 electrons that need a place to go? No, I've only got 4. So I can only draw 4 electrons. So here is where Hund's rule comes into play. As I'm going to put electron, electron, electron. And then one oppositely spinning electron for Pauli's exclusion rule. Pauli's exclusion principle, excuse me. So the electron configuration for oxygen is going to be 1s2, 2s2, 2p4. The 1s and the 2s, the big 1s and 2s, those tell me the energy level, the quantum principal number. The s and the p's tell me the sublevel that it's in. And the superscripts tell me how many electrons there are. 2 plus 2 plus 4. That's 2 plus 2 is 4, plus 4 is 8, and that accounts for the 8 electrons that oxygen has. So now let's look at chlorine. And chlorine has 17 electrons, so this is going to be a little bit longer. So with chlorine, I'm going to start with 1s. So I draw my 1s orbital, and it can hold 2 oppositely spinning electrons. Now I've got 15 electrons that need a home. So after 1s, I go to the next line, and I have the 2s orbital, and it can hold 2 electrons because it's an s orbital. Now I have 13 electrons left. After 2s, I go up to the top of the next line, and I go with 2p. And it can hold 6 electrons, and I've got more than 6, so I go 1, 2, 3, opposite, 4, 5, 6. Now I've got 7 electrons. After the 2p orbital, I go to the 3s orbital, and it can hold 2 electrons. Now I've got 5 electrons left. And then after 3s, I go to 3p. There are 3 orbitals right there. And I'm going to go 1, 2, 3, 4, 5. So my electron configuration, I can write that from my orbital diagram. And it would be 1s2, 2s2, 2p6, 3s2, 3p5. And I can add up those superscripts and double check. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. And chlorine has an atomic number of 17 on the periodic table. So that is how I write an orbital filling diagram and an electron configuration for chlorine. You have to follow the alphabet. So the orbital diagrams have the arrows. And remember, they can never be pointed in the same direction due to the Pauli exclusion principle. And you're going to fill up each orbital on the same sublevel before you go back and give them a pair. So, when I'm talking about noble gas notation, that uses noble gas symbols in brackets to shorten inner electron configurations of other elements. And we're going to be doing that after we get used to writing the ground state electron configurations. So, let's look at strontium. And on the periodic table, strontium has 38 electrons. So, we're going to practice writing the electron configuration without writing the orbital diagram. So, I'm going to start. And I've got 38 electrons, so I'm going to start on my alpha with 1s2. And now I've got 36 electrons I need to hold. Then I'm going to do 2s2. I've got 34. After 2s, I go to 2p, and it can hold 6. So 2p6, and so 34 minus 6 is 28. After 2p, you follow your alpha out and you go to 3s2. And now you've got 26. And then you go to 3p6. And now you've got 20. Now here's where a lot of people make mistakes. Follow the line. After 3p, what do you hit next? You would think it would be 3d, but it's not. It's 4s. So after 3p6, you write 4s2. Now I've got 18 left. And then I go to finally get to 3d, and it holds 10. Now I've got 8 electrons left. And then I follow my line from 3d. I go down to 4p6. Now I've got 2 left. And then after 4p, you follow the line. And you go to 5s. 5s can hold 2, and I have 2 left. So, that would be how I write my electron configuration for strontium. So, when I'm doing that and I'm writing my electron configuration for strontium, I have to make sure I follow the alphabet. We're going to come back and write this noble gas shortcut, and we're going to do that later on. So now what I want you to do is I want you to pause where you're at, and I want you to write the noble gas, not noble gas. This should not say noble gas right here. This should say electron configuration. I want you to write the electron configurations for carbon, zirconium, lead, and uranium. So pause it, write it, and then come back and check it. You better have paused it. I hope you're just checking your answers right now. So when I'm going to write the electron configurations for carbon, I look on the periodic table and carbon's got 6 electrons. So it's going to be 1s2, 2s2, 2p2. If I were going to write its orbital notation, that would be 1s up, down, 2s up, down, 2p. Remember that there are 3 of those, and it would be 1, 2. Zirconium. Zirconium has 40 electrons, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. Alright, lead. Lead's a big one. And when you go find lead, lead has 82, which is a little bit large. So, when I do lead, I'm going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and then I'm going to do 6s2, 6s2, 4f14. You have to pay attention. I almost skipped it. 6s2, 4f15. Oh, nope. Go back. Come on, computer. 4f14, 5d10, 6p2. That one's long. Go through, double check your math. Make sure that all of your superscripts end up adding up to each other. And then uranium. Oh, uranium. Uranium's going to be longer than lead because uranium has 92 electrons on it. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f4. When you add that up, you should get 92. So that is how you write electron configurations and orbital diagrams. Remember, orbital diagrams are the ones with the arrows, and electron configurations are the ones with like 1s2, 2s2, etc. Thanks for watching.